Here's MTI Instruments Director of Business Development, Donald Welch. Don?
Thank you, Rich. I'm Don Welch, Director of Business Development for MTI Instruments, and today we're going to talk about capacitance displacement measurements. What is a capacitance displacement measurement? Well, essentially we set up a field between two plates. One plate is the face of the probe, the center element, and the other one is a grounded target. If we look at the electric field lines there, we can see that the center lines are very straight, going perpendicular into the target. And then we also see fringing fields that are off to the sides, and also one generated by the guard, which we'll talk about in a little bit. What's important about non-contact capacitive displacement measurements is that there's no physical contact between the sensor and the target. So there's no wear, there's no loading, and you also don't have any distortion of the target. Whereas contact probes would push on a target and could actually bend it a little bit. The other interesting thing about capacitive displacements is the very high resolution and accuracy we get. It's very similar to laser interferometer, but at a much lower cost. And it can actually have higher stability than some lasers out there. And the resolution is about as good as a laser interferometer, in some cases higher. What are some of the unique advantages of capacitance displacement measurements? Well, it's got very high resolution. The sensors are passive, they're made out of stainless steel, and we also have precision capacitance amplifier designs. The linearity that we can get and the accuracy are down in the range of 0.01% at speeds of up to 5 kilohertz. The resolution is sensor dependent, so the smaller your sensor, the higher the resolution. We can get down to less than 2.5 nanometers for a 25 micron range sensor. As a sensor gets larger, say example 1,000 microns, then our resolution will be about 100 nanometers. And it is possible to actually get down to less than 1 nanometer with bandwidth limiting and sensor design. One of the biggest accuracy issues related to capacitive displacement measurement is linearity. And if we look at the chart here, we can see a straight line, the blue line, that is very straight, and that's been curve fitted to the black line, which is the actual sensor response. And there's deviation about that blue line, and it's banded by the upper and lower red dotted lines, which would correspond to the linearity that we would see. So the absolute accuracy depends on the linearity and the resolution of the probe, and also the extra errors contributed by the amplifier. We also have very low temperature and time drift electronics, and we can achieve 0.02% linearity or better. A little of the science behind the capacitance measuring principle. Capacitance is equal to the area of the probe times the ratio of the dielectric constant of the medium, which is typically air, to vacuum. In vacuum, it would be 8.8854 picofarads per meter. And typically the difference between air and vacuum is 1-to-1 for all practical purposes. We also have the distance, the gap from the face of the probe, and as that gap increases, then the capacitance is obviously going to get smaller. If we increase the area of the probe, you can see that the capacitance is going to go up. So it's a trade-off between the gap you want to measure and the size of the probe. The other thing we have to deal with is the guard ring on the capacitance probe. A capacitance probe without a guard ring has field distortion. If we look at the probe in the image here, we can see the center electric field is fairly straight, but as you get to the edges of the plate, we have what's called fringing, and the field starts to distort. Well, that contributes to linearity error, and that's bad. So what we want to do is get rid of that fringing effect on the center plate to the target. The way we do that is by adding a guard ring. The guard ring is run at the same potential as the center electrode, and it linearizes the field. If we look at the image here, we can see the measuring field from the center capacitance element is very straight and very linear, and that's what gives us our good linearity down around the range of 0.01%. If we take the guard ring away, it's going to be horrible, probably worse than 10%. The fringe guard also helps extend the field in a straight line so we can sense targets further away. As we talked about before, as part of the capacitive scientific principle, the sensor size is based on the following: sensor measurement range, the measurement resolution, and the guard ring size. Typically the guard ring thickness has to be equal to the gap. We can actually make it a little less than the gap, but good practice, good design practice dictates that the guard ring should be about the same as the gap. The center element, of course, is going to be proportional to the gap. And then we have a third element that's called the body, and that's grounded, and that's how you grip the probe without shorting out the guard ring. Some things we also need to address is the target shape. Different shapes will create fringing effects, and typically we like to have a target that's bigger than the probe. The smallest you want to make a target is about the diameter of the probe. And we also have issues with target flatness, sensor tilt angle, and target shape. For example, a round target's going to create some fringing there. Now, we can still gauge to these objects, but you need to correct them mathematically, and you can contact MTI Instruments for formulas that will help you correct gauging to small targets and also dealing with target tilt. The target material should be electrically grounded to ensure the system accuracy. The ground does not have to be a hardwire ground, although we recommend that. You can also use a low impedance ground path for good accuracy. MTI also has amplifiers that do not require a target ground. That's called the push-pull series. MTI manufactures a large range of different probe styles. We have probes with connectors on them. We have flat style probes to fit in tight spots. We have high temperature probes. We can also make probes that will work in cryogenic and vacuum conditions. And we have a probe that is a ring shape, and that's used for examining internal screw threads. MTI offers two basic styles of amplifiers. We have analog amplifiers, which can be used in legacy systems. They have an analog output for each channel. And we also have a new digital Accumeasure amplifier with a pure digital output, no analog output. Let's talk a little bit about applications of capacitive displacement measurements. A very popular one is piezo flexure. This is where you have a piezoelectric element that has an electric charge applied to it, and it moves a stage. Two stages can be bolted together to get X and Y motion. Our amplifiers are extremely good, and the probes, at measuring down to nanometer resolution. We also have had excellent success with semiconductor wafer thickness and measuring flatness, bow, and warp. MTI has a whole product line called the Semi-Automated and a Proforma 300 that are specifically set up to measure semiconductor wafer thickness. Coplanarity, where you need to ensure, for example, a semiconductor wafer mask alignment. You don't want any tilt on it. You also want to measure the overall height. Lens focusing is another popular application. Autofocusing, where you set the alignment, eliminate lens tilt, and also the focal point. Bearing runout and measuring bearing vibration, where you don't need to actually have an absolute wired ground, hardwired ground. It can still conduct to ground through the ball bearing film, oil film that's in there. Another popular application is lobing and axial and radial runout on hubs for automobiles. We can measure with very high precision the types of defects that manufacturers want to check and ensure that these don't make it to your car. We've also sold capacitance probes that measure to automobile tires. There's a conductive material that's actually in the tire, and we can measure from the face of the probe through the tire back through the hub, which would then be grounded. We also have high temperature probes that are used for disc rotor runout experiments, measurements, some production facilities where we look at coning, thickness, and vibration. Vibration is another popular application. Machinery health monitoring. Our digital Accumeasure amplifier has Ethernet connectivity and USB, so it's ideal for networking a number of systems that could be used in a plant for vibration monitoring. We also do automated inspection, where you're looking at high precision dimensions of parts as they move by on an assembly line. We do critical dimension inspection on rotating objects. You can think of such things as car camshafts, precision parts that are used in automobile engine construction. And recently we've introduced a thread inspection system where we can using a internal thread inspection probe that's got a ring around it. It looks at a 360-degree displacement measurement as it's inserted into the threads, and we can generate a profile as you insert that probe down in the threads to make sure the threads are all there. It's the correct pitch diameter, that the threads don't stop short of where you intended. MTI can also measure non-conductive targets. There's a dielectric constant associated with dielectric targets, and if you know what that dielectric constant is, you can, if you insert this material in the gap between a probe of at a fixed gap where you know the height of the probe above a conducting metal target, you can measure the thickness of the non-conductive material. We also, if you look at our website, we have a number of formulas and techniques for figuring out what the dielectric constant is of your material and how to set your probes up to make this measurement. It's a little bit tricky, but it's possible to do it. Capacitance sensor advantages versus other displacement measurement systems. Well, obviously contact probes are something that a lot of people want to avoid because of the loading and scratching of high precision parts that you're trying to measure. Capacitance has high resolution, high accuracy, and low thermal drift. These are probably the three main features of capacitance gauging. Additionally, we can go practically from absolute zero all the way up to about 1600 degrees C with high temperature probes and cryogenic low temperature vacuum style probes. We're immune to electromagnetic fields. The amplifier designs are quite small, so they can fit in tight places. And of course, we mentioned vacuum compatible. Typically, the capacitance probe itself is inserted in a vacuum, and we don't have to do anything other than make sure that there's no outgassing from the probe. You would then go through a bulkhead feed-through to exit the vacuum vessel and go to an amplifier, which will be in a regular environment. So let's talk about advantages of the MTI digital displacement capacitance system, which has just recently been developed at MTI. MTI's new digital capacitance system has fantastic linearity, in some cases better than 0.01%. It's the most accurate on the market. We have 4 models available: single, dual, 3, and 4 channel units in a very small modular DIN rail mount. It's got multiple range extensions. This means that a probe, such as like a 12 micron probe, can have multiple range extensions, which means I can extend the range by a factor of 2, 3, 4, all the way up to 10. If we look in the probe brochure, it will tell you the maximum range extension that you can achieve. And we can have a range extension for each of the channels. So you can have up to 10 range extensions per channel for each of the 4 channels. Another important point is no preamplifiers needed. We can drive up to about 20 meters of cable without having to add a preamplifier. It's got a very high sample rate, excess of 20,000 samples per second on each of the 4 channels simultaneously. It's got both USB and Ethernet outputs, so you can choose the best communications method for your application. Most importantly, it's pure digital output. There's no ADC required, so you don't have to run into somebody else's analog to digital converter system. You have uncorrupted 24-bit digital data available for your application. We can also synchronize multiple systems if you have a multi-channel application. What's most significant is the filter, frequency response, sample rate, and linearization are all digital. We can change averaging on the fly. You can change your frequency response on the fly. You can change your sample rate and your filters. These are all built in and can be changed to adapt to your application. Software add-ons. We have a number of add-ons that customers can use. We have a basic software that's free, and you can see an example of that in the slide here, where we're looking at the step output from a piezoelectric drive system. And we can get down to, for example, like several nanometers of resolution. We also have a .dll library that can be used to integrate the system in with C++ or C# software. We have a software development kit that we can give you that has a number of the libraries in it and a number of different softwares, including Microsoft.NET software. And recently we've also introduced National Instruments LabVIEW drivers, and we've recently become an alliance partner, and we'll be supporting that with more drivers as time goes on. For example, if we're looking at semiconductor thickness measurement, you don't need any additional A to D converters on the output of your capacitance amplifier. You can correct directly to your real-time operating system or a PC. And you can write wafer thickness measurement software with National Instruments to map your semiconductor wafer. So very few components are needed here to do this. Piezo stage nano motion control. With the addition of a high voltage power amplifier connected to a PC, you can have a complete closed loop system for nano positioning for use in such industries as electronic assembly, flat panel display, etc. And you can take advantage of the National Instruments LabVIEW software that's got PID control built right in, so you can get up and running pretty quickly with off-the-shelf software. You don't have to design everything from scratch like you do with a traditional analog amplifier, and where you have to go through all the algorithms and to set up a closed-loop system. The networking capability of the digital Accumeasure also allows you to connect directly to PLCs or to other implant switches, off-the-shelf switches that you can buy at pretty much any electronics store. This is very useful in plant automation. It keeps your connection costs down. Again, you don't need additional filters and analog to digital converters. For vibration, you can also take advantage of National Instruments software to look at peak-to-peak motion, non-repetitive runout, repetitive runout. And again, the Ethernet connectivity allows you to monitor multiple situations where you might be wanted to be monitoring motion or vibration.
We'd certainly like to say thanks to you and to all of our attendees for spending some time with us today. Now, to find out more information about capacitance displacement measurements, please visit us at mtiinstruments.com. Take care, and we'll talk to you soon.